In programming, just about everything we build sits on top of arrays. But right from the get-go, you've got this fundamental choice to make. Do I use a fixed array or a dynamic one? It sounds simple, but getting this right can make your code fly. Getting it wrong? Well, you could be wasting tons of memory or, even worse, just crashing your program entirely. All right, let's get into it.
Okay, so picture this. We've all been there, right? You need to store a list of, well, anything. Usernames, temperatures, whatever. But you have no clue how many you're going to end up with. Is it 10? Is it 10,000? If you guess too low, your program hits a wall and just breaks. But if you guess way too high, you're just hoarding memory that something else could be using. It's a real balancing act.
So, how did we first solve this? Well, with the original, super straightforward solution, the fixed-sized array. Just think of it like an egg carton. Once you decide it holds a dozen eggs, it will always hold a dozen eggs. You can't add a 13th slot, and you can't take one away. It's rigid, for sure, but that rigidity? That's actually its secret weapon.
The secret sauce for a fixed array is this thing called contiguous memory. All that means is that every single element is stored right next to its neighbor. There are no gaps, it's one long, unbroken line, like houses on a street, all perfectly in a row. And that perfect organization, well, that's what lets a computer find any item almost instantly. So how does that neat row of houses translate into pure speed? Well, the computer is actually pretty clever here. It doesn't have to search for anything. It just does one quick calculation. It knows where the street starts, that's the base address. Then it does some simple math like, okay, I need the 5th item, and each item is this big. It calculates the exact spot, and bam, it jumps right there, instantly. And that, my friends, is what we call O of 1, or constant time access. It is ridiculously fast.
So let's break down the performance here. Access is O of 1, lightning fast, just like we said. And adding an element to the end? Also super fast, if you have an empty spot. But here's the catch. Look at insert and delete. The second you try to stick something in the middle or pull something out, oh boy, you have to shuffle everything after it to fill the gap or make room. And that is a slow, painful ON operation. The takeaway? Fast, but super inflexible.
So yeah, this whole inflexibility thing was a massive headache for developers. It was just asking for trouble. And that frustration, it led to one of the most useful inventions in programming, the dynamic array. This is the magic box that just seems to grow on its own whenever you need more space. It's the powerhouse behind Python's lists, Java's array lists, and C++'s vectors. It's literally everywhere.
I love this analogy because it's just perfect. You just keep adding elements, parking cars one after another. You're not counting spaces, you're not worrying about capacity. Then, the moment you try to add one more and the lot is full, the system handles it all for you behind the scenes. A new, bigger lot appears, all the cars are moved over, and you just carry on like nothing even happened.
Okay, let's see this in action. Here's our little array. It has a capacity of 4, and we filled up all 4 spots. Size is 4, capacity is 4. So far, so good.
But then, the inevitable happens. Our program needs to add just one more thing, the letter E. We're full. There's no more room. So what does the dynamic array do? This is where that behind-the-scenes magic kicks in.
Of course, it's not really magic. It's just a really clever automated process. First, the system quietly goes and creates a brand new, bigger array, usually doubling the capacity. Then comes the grunt work. It has to copy every single element from the old array over to the new one. Then it can finally add our new element, E. And once that's all done, it just gets rid of the original smaller array.
And voila! Look at that. We've successfully added our element, so our size is now 5. But the capacity, that shot up to 8. We have plenty of empty slots for future additions, so we won't have to do that whole resize dance again for a little while.
Now, I know what you're thinking. Hold on, copying everything over sounds really slow. And you're absolutely right. It is. It's an expensive O of N operation. But, and this is the key, it happens pretty rarely. By doubling the capacity each time, the expensive resizes get further and further apart, so you end up with one slow operation followed by a whole bunch of super fast additions. When you average that cost out over time, the price of that one slow operation basically disappears. We call this O of 1 amortized time.
But this incredible flexibility doesn't come for free. In engineering, and especially in programming, there is no free lunch. Every solution has a trade-off, and dynamic arrays are no exception. So let's break down the price you really pay for all this convenience.
To understand the trade-off, you have to get these two terms straight: size and capacity. Size is easy.
It's just how many things are actually in your array right now. Capacity is how many slots the array has reserved in memory. And of course, the size can never ever be bigger than the capacity.
And this chart right here shows the cost perfectly. We're using 5 slots, but we've allocated 8. Those 3 extra slots, that's wasted space, at least for now. Right after a resize, a dynamic array can actually be half empty. That memory overhead is the tax you pay for the convenience of not having to manage the size yourself.
There's also another, sneakier problem. What happens when you delete elements? Should the array shrink to save space? Well, if you shrink it as soon as it's half empty, you can get caught in this nightmare scenario called thrashing. Imagine, you add an item, it grows. You remove one, it shrinks. Add one, it grows. You get the idea. You're stuck in a loop of expensive operations. The smart solution is to only shrink when it's much emptier, say 25% full. This creates a nice buffer zone and prevents that thrashing.
So, we have 2 powerful tools, each with its own strengths and weaknesses. The final question is, how do you choose the right one for your specific problem? Which one should you use?
This cheat sheet pretty much lays it all out. And if you look closely, for a lot of things like access and insertion, they're identical. The real fork in the road is in that append row and the space row. A fixed array is perfectly efficient with memory, but it hits a hard wall when it's full. A dynamic array offers what feels like infinite growth, but you pay for it with that amortized time and the potential memory overhead.
You should reach for a fixed array in some very specific situations, like if you're coding for a tiny embedded system where every single byte counts. Or if you know for an absolute fact that you will only ever have, say, 7 days in a week. It's perfect for that. It's predictable, it's lean, and there are no surprise performance hiccups from resizing.
And for almost everything else, the dynamic array is your best friend. Seriously, if you don't know how much data you'll be handling, if you value convenience and want to avoid those out-of-space errors, the dynamic array is the default correct choice. There's a reason it's the standard in virtually every modern programming language.
Ultimately, the choice comes down to this single question you have to ask yourself. Are you in a situation that demands the absolute, predictable efficiency of a fixed box? Or does your problem require the safe, convenient flexibility of a box that can grow on its own? Understanding that trade-off, well, that's the key to writing better, smarter code.